Okay, let's jump into this table problem, a really famous one on the AP exam, specifically in the FRQ section. It says the velocity of a drone at different times t is a differentiable function, so meaning there's no gaps, there's no holes in our graph, there's no sharp corners, measured in meters per minute. So here we have values of t from 0 to 40, from 0 to 40 minutes, and the different velocities. Part A says, estimate v prime of 21 and interpret it. So v prime of 21, first in my brain, I'm translating that. That means I need the rate of change of velocity, the derivative of velocity at t equals 21. Okay, so if I need the slope of v of t, notice 21 lies between which two t values here? Yeah, it's going to be between 20 and 24. So if I need the slope at 21 and I have values surrounding 21, what math might we do with these two values to get a slope? Keep in mind the key word here is to estimate the slope at 21. So if you said find the slope using 20 and 24, you're correct. So we're going to use MSEC. We're going to, let's say 21 is, if this is 20 and this here is 24, if I want the slope at 21, it's going to be a pretty gosh darn good estimate if I find the slope of the secant line surrounding 21. So MSEC is going to be a pretty good estimate of M tan at t equals 21. That's what we're going to do. So we'll write MSEC equals, okay, if this is A, let's make this A, let's make this B. Then we're going to have V of 24 minus V of 20 over 24 minus 20. V of 24 is negative 220, that's the Y value, minus V of 20, which is 240, all over 24 minus 20. So my numerator will be negative 460 over 4. How many times does 4 go into 460? Don't know, but we can find out. Negative 115. Now, that's our first part of our answer. So let's write v prime of 21 is approximately negative 115, but we need, it says use proper unit. If our velocity is in meters per minute, I'm looking right here, then the slope of that will be meters per minute, so per minute squared. Here we've shown our computations and we've written our answer. Okay, what we didn't do yet is interpret. So here's our interpretation. We can do this in two ways. We can use this v prime interpretation, in which case we would say the rate of change, just like we did earlier, of velocity. Of the velocity of what? Of the velocity of the drone at t equals 21 is negative 115 meters per minute squared. Okay, that's interpretation number 1. Interpretation number 2 could go like this. Instead of v prime, you might think of it as a. This is acceleration. So you could say a of 21 is negative 115 meters per minute squared. Therefore, the acceleration of the drone at t equals 21 is negative 115 meters per minute squared. So we could have done number 1 or number 2. Either of these is proper interpretation and also the correct answer. B says from 0 to 20 minutes. Okay, so let's highlight from 0 to 20. Why must there be some time t at which the acceleration of the drone is 12 meters per minute squared? So here's what's going through my head as soon as I read this problem. If I'm given velocity. And I'm asked to prove that there is some acceleration that equals, the acceleration is 12 meters per minute squared. They're asking me to deal with the slope. They're asking me to deal with the derivative. And anytime they're asking me, prove why there must be some t in that language, what they're getting at here is the MVT. With the mean value theorem, because they're asking me to deal with slopes. So remember, MVT, because of the M, that's how I remember it's slopes. Whereas the IVT deals with the value itself, like just the y value. So let me write down the example. If it had said, why must there be some time t where the velocity is 12 meters, then I would realize that this is just well, they're giving me velocity, they're asking about velocity, so this is a y value problem, right? They're just asking me to prove that somewhere in here, the y values there, it equals 12. That would be an IVT problem. Since they're asking me for the slopes, they're asking me about acceleration, aka v dash, I know I'm doing MVT. So very straightforward MVT. Hopefully you have it memorized. It goes like this. Since, okay, so when we're dealing with slopes, we have two conditions. The first one is always that it's continuous, but the second one, when we're dealing with slopes, we have to say it's differentiable. So since v of t is continuous on the closed interval, okay, so we can just end with saying m sec equals m tan, but then we need to actually show the work. By the way, I knew that this was differentiable because it told me right up here. Let's show our work. M sec equals m tan. Well, m sec would be v of 20 minus v of 0 over 20 minus 0. And m tan would be v prime. And our job is to prove that the acceleration is 12 at some point in between. So don't put the 12 in here because then you're saying the time is 12. But it says here the acceleration is 12. So we want to just prove that there is some time t, which we can prove for, that it's going to equal 12 at the end. And that will happen if you've done this correctly. So let's find v of 20 is 240. V of 0 is 0 over 20 minus 0. So that's 240 over 20, which is indeed 12. And so we've proved it, that there is some time between 0 and 20 where the acceleration is 12. How do we know? Because from 0 to 20, the average slope, right, the slope of the secant line was 12. So we know somewhere along there, the slope of the tangent line also equals 12.